starting the recording. All right. Now, before we get started into today's discussion, we need to look at a table real quick because we're going to carry this information into today and tomorrow's discussion. Okay? So we have to recall our three or four, I guess, three main calculatable, if that's a word, calculable. Yep, sure. Items when we are looking at series and parallel. For current in a series diagram, remember the current will be the same for each resistor. For parallel, it's the sum of the currents. Potential difference. In a series, it's going to be the sum of the potential differences. In parallel, it's the same for each resistor. So basically, current and potential difference just flip-flop. And to calculate equivalent resistance, excuse me, the sum of individual resistances for series and the reciprocal sum of the resistances for parallel. All right. You can always reference back to that if need be. Let's talk about what we're doing today and tomorrow. We're doing complex resistor combinations. Today, we are going to be essentially calculating equivalent resistance. Let me make sure that in a complex circuit. Tomorrow, we are going to be looking at the current in and potential difference across certain resistors. So today we're going to be kind of working forward. Tomorrow we're going to be working backwards. Okay? So it is kind of like a puzzle, if you will. Okay? Where you got to break these complex combinations of parallel and series circuitry and break them down into smaller units. Okay? So today, like I said, we're going to calculate the equivalent resistance for complex circuit involving both series and parallel. Tomorrow, we will do the current in and potential across individual elements. So many complex circuits can be understood by isolating segments that are in series or in parallel and by simplifying them. Okay? Now, we have a series like this. Not series, a complex diagram like this, where we have series and parallel elements together. How do we solve the equivalent resistance of this complex circuitry? Well, one of the easiest things that we're going to do, you might have different ways. One of the easiest things we're going to do, and you're going to see it, is we're going to make this setup more linear in appearance. So we're going to take it out of its connection from the battery. Because to calculate equivalent resistance, we really don't need it today. So we're going to disconnect our wires from the battery. We're going to put them in more of a linear fashion. We are then going to come up with a plan of attack, meaning we're going to group things that are similar in series or parallel, and we're going to solve them one at a time and break it down to where we will only have one equivalent resistor that represents all of those combined on that circuit. So, blah, 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 blah. As I mentioned, disconnect the wires from the battery. Place it in a more linear fashion. And then begin grouping your like resistors together. For instance, these two, the 3 and the 6, how are they wired together? Series. Very good. What about the 6 and the 2? Series. Aha. But then, look at these two. How are they wired? Parallel. Then you have this lonesome little one over here. So we're gonna leave that one to last. Now, as you go through this, you're gonna start combining. Okay, and you'll see it as we go through this. So again, we have our first step. We group the 3 and the 6 together. We get our 9. Right? 3 plus 6 is 9. Yes. Our second step, our second group. The 6 and 2. 6 and 2 is 8. Very good. See, I told you you could do this. 8. So again, why are we able to add those up? The 6 and the 3 and the 6 and the 2. Because they're wired in series, and the equivalent resistance in series is simply just summed up. But now look what we got here. We have the equivalent resistance here for the 6 and 2 and the 4 ohm resistor. Those are in parallel. So how do we solve that again? We have to take the reciprocal sum. Okay? So eventually we get there. Again, my computer doesn't like to show, or my program doesn't like to show this correctly. But yes, you take the reciprocal sum of that, and you find that it's 2.7 ohms for this parallel circuit. Well, again, every single calculation that we do has been subtly reducing that complex circuit. It's simplifying it. So we get 2.7 here. Now look at all 3 of these. How are they now wired? Series. Now, it's not like you are rewiring everything, every calculation you make, but you are mathematically simplifying this. So since these are in series, how do we find the equivalent resistance across the entire circuit? We simply add them up. We get 12.7. So as you can imagine, depending on how you do this. Now, I think by now you know that I like to try and show as much as possible step-by-step methods in order to solve certain questions, okay? You might come up with a quicker solution. That's fine, okay? I personally, when I do this stuff, I like to draw my circuit step by step. You don't have to, unless asked, okay? Because it is a good practice for you, but not 100% required. So let's look at a couple other problems, okay? Now, let's get out of here. Get your book out. And turn to page 659. 659. Oops. There we go. All right. Page 659. All right. We're going to do a couple of these. Now, in order to save space, they kind of just label them. Here, let me zoom in real quick. They kind of just label them very generically as resistor A, B, and C, so on and so forth. Okay. And in the problem itself, it gives you the various resistors to use. So let's look at 1A. Again, we are to use this particular diagram. Let's see, I'm going to rewrite it here. And you don't have to be an artist like myself in order to do this. Okay, and ohm, fantastic. And then 2. Okay, that's close enough. So they want us to use the following resistor resistors with the following resistances. So RA is 25.0 ohm. RB is 3.0 ohm. And RC is 40.0 ohm. And so really, in order to make this a little more simplified, again, this is kind of a simple one in general. The ones for your homework you might see that are a little more tiered, okay? If you want to, you can just make this the equivalent of this, where you have 25, 40, and 3, okay? So again, I just simplified this. And so I'm going to start simplifying or breaking it down into groups. So this will be my group A, because I really can't do anything with just this lonesome 25 out here. Mathematically, I can only do something with here. And then I'll use this as my group B. Okay? So I'm going to solve for the parallel circuitry first. So I'm going to set it up like this. REQ is equal to 1 over 1 over 3 plus 1 over 40. And again, the reciprocal. I want you, since we've done quite a bit of this, I want you to solve the equivalent resistance for group A. You already got it? No, we're doing it step by step. I know he said he's got it, but I still want you to do it. I'm going to come to you for the answer for this part. That's why we do this. All right, sir. Oh, very good. Very good. Very good. 2.8 ohm for group A. And if I were to redraw this schematic diagram, now that I've simplified that, you'd have this, where we'd have 25 ohm here, 2.8 ohm here. And so this is my group B. So equivalent resistance is going to be 25 ohm plus 2.8 ohm. And Sir Flannel? Very good. And so, simplified, we've got this diagram. So yeah, these are short. We're gonna do one more, but these are short. Okay. Like I said, you might have a little bit longer ones in your homework. Now let's look at 2A as well. And I'm going to go ahead and, to save space, I'm going to go ahead and simplify this. So 2A's set up a little differently. So we're going to have the following linear setup. And then we got another. Okay. My drawings are so good. So we've got 25.0 ohms here on this one. We have 3.0 ohm on that one. We've got 40 on that center one there. And for D, we've got 15.0. And for E, we've got 18.0. So again, splitting these into groups, I'll call that A. I'll call this B. Then I'll call this C. You could do it a couple different ways. You could call this A, and then this C, and then, or this B, and then this C. But I like to try to keep things in similar fashions when we do this here. So for group A, okay, same thing. It's in what? Series or parallel? Huh? Group A right here? Parallel. So you take the reciprocal again. So you're going to get the same thing. Nope, I'm looking at the wrong one. Just kidding. Yeah, I was looking at the wrong problem. 25. Okay. So what do you get for group A? 2.7 ohms. Very good. Okay. Now I've got 2.7, 40, and then we got 18 and 15 here. So I just redrew it. Now again, you could make this a group and this a group, but eventually you're still going to have to add everything up. So that's why I called this group Group B. So again, same thing. Equivalent resistance for Group B. 1 over 18 plus 1 over 15. Reciprocal that. What do you get? 8.2 ohms. Very good. So now this gives me 2.7, 40, 8.2. And so for group C, which is everything else left here, you have basically 2.7 plus 40 plus 8.2. What is the equivalent resistance? 50.9 ohms. In a simplified circuit, looks like this. Questions on this? Okay. So I'm going to hand out your homework. When you are done, I would like it submitted to Classroom. Okay. And I will tell you what problems to do. All right. Your homework for this evening are questions. So you can circle these. 1, 4, 5, and 7. 1, 4, 5, and 7.